the invisible force that is slowing down Earth and why scientists are terrified. The trading floor screens freeze for half a second, then a full second. Orders hang. Across orbit, a satellite's clock disagrees by 4 milliseconds, and its fix jumps a dozen meters. In a basement lab, an alarm flashes. UT1 out of spec. Timekeepers whisper a phrase nobody has ever implemented: negative leap second. Get this, Earth is slowing down, except sometimes it speeds up, and our clocks hate both. Tides drag on the planet, melting ice shifts mass. Winds and ocean currents trade spin with the crust. Underfoot, the core tugs back. GPS, finance, and the internet survive on perfect time. To understand the drift, we need to rewind. The first clue, clocks versus the planet. The first clue arrived not in a telescope, but in a vacuum chamber. Atomic clocks count the tick of atoms, cesium or ytterbium flipping states, with a precision that makes a heartbeat look like geologic time. In the 1960s, timekeepers built a new scale from these ticks, a steady river called International Atomic Time, TAI. Then they faced an awkward truth: Earth's rotation, the thing humans long used to define a day, wanders. They needed a compromise for civil life. Coordinated Universal Time, UTC, would match atomic regularity, but be nudged to stay close to the planet. The nudge was small. If Earth's rotational time, UT1, drifted more than 9/10 of a second away, they'd add an extra second to UTC. That was the invention of the leap second in 1972. The first years were busy. 2 seconds added in 1972 alone, then more at irregular intervals, because the long-term trend since the 19th century was simple. Days, on average, were getting longer by tiny fractions due to tidal friction. At first, the fix seemed elegant, but elegant on paper can be brutal in code. Leap seconds are rare and unpredictable far in advance. They aren't like leap days on a calendar. You learn about them months ahead and only sometimes. For software that expects time to move forward smoothly and monotonically, a minute that sometimes lasts 61 seconds is a trap. In 2012, that trap snapped shut. Linux systems saw the extra second and some spun their CPUs into a storm. Reddit went down. Airline bookings stalled in Australia. In 2017, a sliver of Cloudflare's DNS infrastructure misread time offsets and treated time as moving backward, triggering a crash in part of their network. Almost every time we have a leap second, we find something, Linus Torvalds said, because no one tests code for a moment that hardly ever happens. Stakes were clearer now. GPS satellites rely on synchronized clocks to triangulate positions. A few billionths of a second smeared wrong means meters of error on the ground. High-frequency trading firms co-locate servers to shave microseconds. An offset can mean money lost in the span of a key press. Power grids watch frequency and phase. Telecom networks repeat time pulses. Databases expect order. The leap second was a band-aid on a moving target. But if UTC and UT1 were diverging, the next question was obvious. How do we actually know what UT1 is doing, second by second? The answer is quietly dramatic. A global network of radio telescopes listens to quasars, ancient beacons near the edge of the observable universe. By timing the arrival of the same quasars' radio waves at dishes separated by continents, very long baseline interferometry, the network pins Earth's exact orientation in space. You can watch the planet wobble, precess, and subtly speed up or slow down. In the control room of a timing lab, that data turns into a heartbeat graph, length of day, or LOD. It's nominally 86,400 seconds, but the line breathes. Storm seasons add or subtract a fraction of a millisecond. Major El Niño events leave a fingerprint. Even earthquakes can nudge the line by microseconds. And then there are the decadal swings tied to the deep interior, signals that no weather map explains. Meanwhile, atomic time doesn't care. TI marches on, ruthlessly even. UTC tries to thread the needle between the two. Every leap second is a public negotiation between messy nature and perfect machines. Then came a twist. Around the early 2020s, the average day frequently dipped closer to or slightly below the textbook length, June 29, 2022. Even set a record at about 1.59 milliseconds short. Earth's crust seemed to be spinning a touch faster at times. For timekeepers, that raised a specter no one had ever implemented, a potential negative leap second, which would mean removing a second from UTC to let UT1 catch up if the trend persisted. Engineers hated the prospect. If adding a second breaks things, subtracting one, time skipping, could be worse. Agencies and companies started making a case for stability over purity. Meta, Google, Amazon, Microsoft pushed to abolish leap seconds altogether. National labs listened. In 2022, member states at the General Conference on Weights and Measures adopted a resolution to relax the rule by or before 2035. Allow UTC to drift farther from UT1 before any correction, on the order of decades to a century. That would turn a spray of unpredictable 1-second jolts into a planned generational correction. But even as the policy shifted, the science kept complicating the story. Clocks had exposed the drift. Telescopes mapped the wobble. Yet the causes stacked like gears inside gears. The tides, yes, always stealing spin and feeding the moon's outward drift. The atmosphere trading angular momentum with the crust. The oceans, not passive but pushing back with currents and resonances. The mantle and core, a concealed engine making decadal kinks. And on top of that, humans moving water, pumping aquifers, melting ice sheets, subtly changing Earth's moment of inertia. Back in the lab, a technician's pager buzzes at 2:17 a.m. A timing daemon throws a warning. NTP servers see an offset building faster than expected. It's not a leap second night, it's weather and wind, and the network must decide whether to trust its oscillator or the outside world. 20 minutes later, the graphs settle. Crisis averted, this time. That's the uneasy truth the clock's uncovered. The planet is a bad metronome, and we built a civilization on instruments that need a great one. So the chase begins. What's actually pushing on Earth's spin, and why does the push change? To find out, we have to follow the oldest torque of all, the ancient brake, tides as a torque. To understand the oldest hand on Earth's shoulder, go to the shoreline at moonrise. The ocean bulges toward the moon, and because water has inertia, the bulge doesn't stay perfectly lined up. Friction with the seafloor and the continents makes it lag a little. That tiny lag is everything. The rotating Earth drags the bulge ahead like a handle. The moon's gravity tugs back on that handle and applies a braking torque on Earth's spin. At the same time, the bulge pulls the moon forward in its orbit, giving it a small push outward. Stakes first. Tides aren't just pretty charts on harbor walls. That lagging bulge siphons rotational energy from the crust and turns it into heat in shallow seas and turbulence in straits. It lengthens the day by milliseconds per century. On human timescales, that sounds harmless. On geological timescales, it rewrites the calendar. If you care about how navigators set off, how farmers read seasons, how satellites calculate passes, this braking matters. It's the long, slow background that every other wobble rides on. What actually happens is straightforward physics with messy geography. Earth rotates once in roughly 24 hours. The moon orbits in about 27.3 days. The tidal bulge wants to align with the moon, but friction makes it lag slightly eastward. Picture a grip on a spinning wheel. The grip slows the wheel and transfers spin to the thing pulling on it. The energy lost by Earth doesn't vanish. It becomes heat in the tides and orbital energy that nudges the moon outward at a measured rate of about 3.8 centimeters per year, confirmed by laser ranging to retroreflectors left by Apollo astronauts. Meanwhile, the day lengthens. The amount is small year to year, but counted up over millions of years, and it's huge. Evidence isn't just theory, it's fossils and scribes. Ancient corals lay down daily growth bands within seasonal rings. When paleontologist John Wells counted bands in Devonian corals, he found about 400 daily layers per annual cycle. That implies shorter days and more of them per year, because the year's length in seconds set by Earth's orbit hasn't changed much, but the length of the day has. And then there are eclipse records etched into bone and bamboo. Astronomers reconstruct where shadows should have fallen centuries ago. If Earth had spun at today's rate, those eclipses wouldn't match the locations recorded in China and the Middle East. They do match when you allow for a longer day now than then. The moon's recession and Earth's slowdown show up in both coral diaries and human notes. The impact of this slow break shows up in energy budgets too. Tidal dissipation is a power drain on the order of terawatts, comparable to humanity's energy use. Most of that dissipation happens in shallow seas and around rough topography, where currents shear and mix, places like the North Atlantic shelves and the Indonesian throughflow. That's where the ocean's brake pads really heat up. And the heat isn't the main story, the torque is. It's the torque that feeds angular momentum into the lunar orbit and out of Earth's spin. Here's where the human element makes it vivid. For Polynesian navigators, tides were a living calendar. You didn't need equations to know that the sea breathes with the moon. Canoes left with the turning of the current. A village timed reef foraging for the lowest spring tide. A fisherman learned to hear in the swell when a king tide was coming. The same cycle that slowed Earth's spin guided a route between islands. But this break isn't smooth. Coastlines aren't uniform, and ocean basins have resonant frequencies. Some seas ring like drums when the lunar forcing matches their natural slosh period. In those hotspots, the tidal range and the friction amplify, and the torque on the planet is stronger. The Bay of Fundy's extreme tides aren't just scenic. They're part of the imbalance that makes some regions disproportionately responsible for the global slowdown. Elsewhere, the geometry damps tides and the break is weaker. The total is a sum of wildly unequal parts. Complication. If tides have been slowing Earth for billions of years, why does the day length dance around the trend? Because the tide is only one term. There's glacial rebound lifting continents, shifting mass toward or away from the rotation axis. There's the atmosphere, with jet streams that speed and slow and swap angular momentum with the crust. There are ocean currents that torque the solid Earth seasonally and on El Niño timescales. And there's the core, where fluid iron stirs on decade scales and sends a signal up as faint changes in day length. All these sit atop the ancient break, sometimes masking it, sometimes adding to it. So the slowdown you see in fossil corals, extra days per year, is the long arc. The jitter you see in the quasar measurements is the near-term noise. The moon's ledger demands a longer day on average, but coastlines change, ice loads come and go, and basins retune. In the modern era, humans are adding a twist, changing shelves by building, dredging, and damming, raising sea levels that alter where tides break their energy, and pouring new fresh water into the oceans that shifts mass. Even the tidal torque is mobile. This was the first culprit timekeepers could name with confidence, a torque that never sleeps, subtle but relentless. But once you accept tides as the ancient break, a new question opens. Why does the slowdown wobble so much from one decade to the next? To find that answer, you have to go deeper into the planet's hidden machinery, where liquid metal turns and pulls on the crust. The hidden hand, the core-mantle tug-of-war. While the oceans grind away at the edges, something deeper is turning the dial. The core isn't a solid flywheel, it's a layered engine. Under the mantle sits a liquid outer core of molten iron, and inside that, a solid inner core the size of the moon. They all rotate, but not always together, and tiny differences in their motion leak up as changes in day length. This is where the decadal kinks come from. Stakes first. If decadal variability is born in the deep interior, it's fundamentally hard to forecast. Timekeepers can schedule leap seconds only months ahead. A wrong call ripples across satellites, exchanges, and grids. When the interior speeds the crust by fractions of a millisecond for years, the UT1 trajectory curves away from expectations. The world's duct tape for time becomes guesswork. What actually happens is an exchange of angular momentum across boundaries. Fluid in the outer core circulates under the geodynamo, the process that builds Earth's magnetic field. Those flows feel the core-mantle boundary as a rough conductive interface. Magnetic field lines thread the liquid iron and anchor into the lower mantle. When the flow drags the field, it exerts an electromagnetic torque on the mantle. There's also topographic coupling. Any bumps at the boundary let turbulent fluid push mechanically. Over years to decades, these torques add or subtract a whisker of spin from the mantle and crust, and we notice it as the length of day breathing by a millisecond or so. Seismology gave the mystery a face. In the 1990s, geophysicists started comparing pairs of earthquakes that ruptured nearly the same fault patch, repeating quakes. The seismic waves took almost identical paths through Earth, so any travel time changes hinted at a shifting interior. Over years, some waves arrived a sliver earlier or later than expected if the inner core were locked to the mantle. The interpretation: the inner core rotates a little differently, sometimes faster, sometimes slower, relative to the mantle. Recent work has proposed a multi-decadal oscillation, on the order of 6 to 7 decades, with evidence that the inner core's relative rotation slowed, paused, or may have reversed sign around the early 1970s, and again in the early 2000s to early 2020s. Meanwhile, magnetic field records show a roughly 60-year signal. The LOD record carries a similar beat. It looks like a coupled system: inner core, outer core, mantle, crust, exchanging angular momentum and energy. Impact: when the core transfers angular momentum to the mantle, the crust spins up, shaving microseconds off each day. When the transfer reverses, days lengthen. The amplitude is small but persistent, and it stacks on top of the tidal trend and the climate-driven wiggles. For timekeeping, that means a background tide you can't see with a barometer or satellite image. It bends the UT1 curve quietly until the quasar network says we're off. For models, it means you can't predict far without getting the core right. Meanwhile, something else was happening in 2017. In a windowless office, a geophysicist stared at the Allied line and saw a subtle kink. Day-to-day noise smoothed out, but the trend angle changed. It wasn't El Nino, it wasn't storms. The magnetometer data from observatories hinted at a core flow shift. Emails went around. Check the electromagnetic torque terms. Weeks later, the analysis converged. The decadal component had turned. It won't make headlines, but it changed when timekeepers expected the next leap second discussion. Why does the inner core's rotation drift at all? Think of the outer core as a conductor moving in a magnetic field. That motion generates forces that act back on the flow, Lorentz forces. The flow interacts with irregularities on the core-mantle boundary and with subtle density contrast in the lower mantle. Gravitational coupling tries to keep the inner core aligned with mantle mass anomalies. None of these couplings is strong enough to lock the layers together, so they slip, lag, and lead, trading tiny packets of angular momentum over years. Add the geodynamo's variability, and you get a natural oscillator with a period measured in decades. Complication: mantle convection also shifts mass laterally on long timescales. As hot rock rises and cold rock sinks, the planet's figure axis and principal moments of inertia evolve. That feeds true polar wander, small drifts of the crust relative to Earth's spin axis, and nudges lie. It's slower than weather, faster than continents moving. Layer this under the core oscillation and over the tidal break, and the signal becomes a braid. Now add humans. Melting ice and pumping groundwater move mass toward the equator, lengthening days. That trend can oppose a core-driven speed-up. In the short term, the atmosphere can overwhelm both. In some years, winds add enough angular momentum to the air that the solid Earth slows by a few tenths of a millisecond. In others, the opposite happens. The deep engine sets the tempo. Climate plays the melody. Tides provide the drone. The impact downstream is timing chaos if you don't respect all three. Earth orientation parameters, the numbers that tell satellites exactly how Earth is tilted and how fast it's spinning, must be updated constantly. Modern systems ingest those updates like oxygen. When the core tweaks the phase, everything else shifts a beat. This was the moment everything changed for our story's arc. The ancient break is real, but the hidden hand can nudge the minute hand faster or slower for a decade at a time. And the surface is changing too, at a pace the core can't predict. Ice, water, air moving mass around. The tug-of-war doesn't end, it gets crowded. Next, the surface starts to tip the balance in ways we can measure from space. Melting the planet's balance, water moves, time moves. While the core hums, the surface is hauling mass around like a moving crew that never sleeps. And mass in motion changes everything about rotation. Shift weight outward from the axis, and the spinning body slows. Tuck it in, and it speeds up. That's a figure skater, but it's also a planet. Since the 1990s, the water ledger has tilted. Ice is leaving high ground. Aquifers are being pumped. Seas are rising, unevenly. Each transfer edits Earth's moment of inertia and leaves a mark on the length of day. Stakes first. This isn't just climate graphs and seawalls. It's nanoseconds multiplied by billions of ticks per day, adding up to real offsets in UT1 that time. Services have to chase. If the mass drift is large enough, the leap second schedule gets pushed or pulled. And because the edits are sustained, they steer the background slope of the clock fight. Human water use becomes a line item in the planet's spin budget. What actually happens is being watched from orbit. In 2002, two identical satellites started chasing each other around the Earth, linked by a microwave-ranging beam, so sensitive it could sense a change in separation smaller than a human hair. That mission, GRACE, 2002 to 2017, followed by GRACE-FO, starting in 2018, maps tiny fluctuations in Earth's gravity field caused by mass moving below. Stack months of those maps and you get time-lapse geology. Greenland's ice sheet thinning, West Antarctica's basins losing weight, the fingerprint of monsoon cycles filling and draining groundwater, the ocean's mass rising, not uniformly, but with regional humps shaped by winds and currents. Each of those shifts tells the same mechanical story. Move water from near the poles to the oceans at lower latitudes. and you push mass farther from the rotation axis. That increases the moment of inertia. Because angular momentum for the whole Earth system is nearly conserved, the solid Earth's rotation must slow a little. You can see it in the length of day series after you subtract the fast. Atmospheric and oceanic wiggles. A persistent component that tracks post-1990s melt and pumping. Meanwhile, the bedrock under old ice is still rebounding from the last ice age. Glacial isostatic adjustment is the planet's long exhale. As Canada and Scandinavia rise and peripheral forebulges sink, mass distribution changes. That affects gravity measurements and slightly the rotation. It's why GRACE maps need careful corrections. GIA is a loud signal in the data, but it also means the rotation record carries a memory of ancient ice slowly fading. Impact. Every gigaton of ice lost from Greenland doesn't just raise seas, it lengthens the day by a whisper. Alone, it's microseconds spread over years. Together, with Antarctica's losses, with sustained groundwater depletion in regions like northern India, California's Central Valley, and Western Asia, the whispers add up. In 2023, a peer-reviewed study showed that multi-decadal groundwater pumping shifted Earth's rotational pole by centimeters and measurably altered the seasonal wobble. Timekeepers care less about the pole's path than the axial spin, but the cause is the same. We are moving weight. There's another twist. Sea level rise isn't flat like a bathtub. Winds, currents, and the shape of the gravity field sculpt it. That matters because the tidal break depends on where shallow waters and continental shelves focus friction. Raise sea level, and you change the depth and reach of shelf seas. Some hotspots where tides dissipate power. Think the North Atlantic shelves or Indonesian passages could intensify or shift their torque as geometries evolve. The ancient break is being retuned by modern melt. Now, the human element. A water manager in a mega drought signs off on a deeper draw from an aquifer the size of a state. Wells run, canals flow, and the water heads to crops and cities, then to rivers and out to sea. Locally, it's survival. Globally, a few thousand billion kilograms of mass just migrated toward the equator. No one at that meeting mentions the length of day. But in a timing lab, months later, analysts scrubbing the LOD curve will file a note. The interannual residual tracks the terrestrial water storage anomaly. GRACE and GRACE-FO make it visceral with numbers, but you can feel it in other places. Tide gauges read higher at some coasts than others because land is sinking or rising. Winds are piling water up, and gravity is pulling more strongly where ice remains. Satellites see the sea surface tilt. Altimeters write the line. And all the while, the effective radius of mass is creeping outward. Complication. Water's not the only mover. The atmosphere and oceans keep trading angular momentum on weekly to yearly scales, sometimes masking the water-driven trend. El Niño years stand out when zonal winds shift and the air's spin rises, slowing the crust by tenths of a millisecond. La Niña years often flip the sign. To isolate the melt and pumping effect, you have to model and subtract AAM and OAM contributions and correct for GIA. When you do, the residual says the same thing. The 21st century is writing water into time. The meaning for the clock fight is sharp. Duncan Agnew and others pointed out that recent mass redistribution likely postponed the need for a negative leap second by a few years, even while deep Earth effects tried to speed the crust. In other words, climate and water policy now modulate the timing of the most sensitive software update in the world. We become part of the invisible force. Meanwhile, something else rises and falls every day and every season: the air itself. Winds don't just blow, they pick up and put down spin. If water moves time slowly, the atmosphere can shove it fast, and the fingerprints of that exchange show up right in the tick of our clocks. The breathing sky, winds, pressure, and AAM. The air looks weightless, but it carries spin like a hidden flywheel. When winds strengthen in the westerly jet streams, the atmosphere's axial angular momentum, AAM, rises. Conservation does the rest. If the air speeds up eastward, the solid Earth must slow down a hair so the total stays nearly constant. Reverse the winds, and the crust gets that sliver of spin back. It's a handshake across an invisible boundary, and you can read it in the day's length, almost in real time. Stakes first. This is the fastest lever on the clock outside of earthquakes. AAM swings can add or subtract tenths of a millisecond from LOD over weeks. That's enough to skew UT1 predictions, which feed Earth orientation parameters that satellites depend on. Miss an AAM surge and your autonomous tractor draws crooked rows. Your aircraft's inertial system drifts slightly more before GPS fixes it. Your trading timestamp slips under audit. The atmosphere's breath becomes everyone's problem when systems expect time to be smooth. What actually happens follows the wind belts. The subtropical jets strengthen, the polar jets shift latitude, and pressure systems shuffle mass around. AAM has two pieces: winds themselves and pressure loading on Earth's surface. Both change where angular momentum sits inside the Earth atmosphere system. During strong Madden, Julian oscillation bursts, a 30 to 60-day pulse of tropical storms and convection. You see a matched rhythm. AAM climbs, LIDE lengthens by roughly 0.2 to 0.4 milliseconds. During major El Niño events, the Pacific's coupled ocean atmosphere engine pushes the subtropical jets harder and farther east. AAM rises and stays elevated for months. The clocks hear it. Impact. The fingerprints are clear. In 1997 to 1998, as a powerful El Niño matured, daily AAM and LIDE marched almost in phase. Time services saw the crust give up spin to the air and had to correct UT1 more aggressively. In 2015 to 2016, a different flavor, a strong but distinct El Niño, again pushed AAM high, and the length of day followed. The message is simple. Climate modes aren't just temperatures and rainfall, they're torque. Meanwhile, something else was happening over the poles. Sudden stratospheric warmings, the wintertime collapses of the polar vortex, rearrange high-altitude winds in days. When that vortex weakens and the zonal flow reverses, the AAM budget takes a hit. The crust feels a small but sharp nudge. Timekeepers see a kink in their short-term forecasts and scramble to ingest fresh atmospheric data. Even a single event can bend the UT1 trajectory enough to matter for satellite scheduling windows. Here's a micro story from the weather desk. A national forecast center kept finding a persistent bias. Models were off by a fraction of a second in phase when verifying jet streak timing. The culprit wasn't code, it was timing. Their in-house time distribution had drifted against UTC by microseconds in a week of bad NTP discipline. That tiny offset multiplied through assimilation cycles and matched with a period when AAM was ramping, produced a consistent phase error. Fixed the clock path. The bias vanished. The sky's torque was never the problem. Human timing was. Complication. AAM doesn't act alone. The oceans sling angular momentum too. OAM, when basin-scale currents speed up and when pressure builds over gyres. Their exchanges with the crust can reinforce or cancel the atmospheric signal on monthly to yearly timescales. During some La Niña years, stronger trade winds pump the oceanic subtropical cells and shift current patterns so that OAM and AAM partly offset and LO die. Other times, they stack and the day swings farther than expected. Separating them requires models and data streams that talk to each other quickly. But there was one problem for leap-second planning. AAM is predictable only to a point. Yes, forecasters can project jet anomalies weeks ahead, and some climate patterns give seasonal heads-up. Yet the exact phasing of wind bursts, stratospheric disruptions, and mid-latitude storm tracks means the high-frequency LOD wiggles won't line up perfectly with any schedule. You can smear a leap second across a day in software to reduce risk, but you can't schedule nature. What nobody knew at first was how much human-driven climate change would modulate this exchange. Warmer oceans shift tropical convection zones. Jet streams wobble differently in a warming Arctic. The statistics of El Niño and La Niña may be trending toward more frequent mixed events. Those shifts rewrite variability, which writes into UT1. The chain is long, but the ink is wet right now. In the aftermath of each AAM surge, timekeepers publish revised Earth orientation parameters, and the world's navigation systems drink them in. The pipeline is a lifeline. Predict, measure, update, distribute. Miss a beat and the error multiplies through fleets and farms. While that was happening over our heads, another fluid was pushing back. Below. The oceans don't just break under the moon, they slosh, resonate, and torque the crust in their own rhythm. Their story is slower than a storm, but steadier than the stratosphere, and some coastlines make the torque roar. The restless ocean. Currents, seiches, and resonance. If the atmosphere is a quick breath, the oceans are a steady push. They don't just carry heat, they carry angular momentum. When currents accelerate eastward, they store a little more spin. Conservation takes over. the solid Earth slows by a hair. When currents weaken or shift westward, the crust gets that sliver back. Layer that on tidal friction, and you get a constant low-frequency torque that timekeepers can't ignore. Stakes first. Ocean-driven changes don't announce themselves with headlines. They creep. Miss them, and your UT1 forecast drifts across months. Satellite operators miss narrow windows. Precision agriculture drifts rows by centimeters that become costly rework. The ocean's torque shows up in the same clock, feeds guiding aviation, surveying, and autonomous systems. Ignore a basin's slow turn, and your entire timing chain inherits its bias. What actually happens lives in boundaries and basins. Western boundary currents, like the Gulf Stream and the Kuroshio, race north with steep gradients. Their inertia and pressure fields load the crust. Internal pressure anomalies over subtropical gyres act like slow pistons, pushing and easing against the solid Earth. When trade winds spin up the gyres, oceanic angular momentum rises, the day lengthens subtly. When gyres slacken, momentum drains back to the crust, days shorten. It doesn't take big speed changes. It takes mass spread over thousands of kilometers, moving coherently. Meanwhile, the ocean has its own resonances. Tides aren't only deep ocean bulges, they're amplified in marginal seas whose natural slosh periods line up with lunar forcing. The North Sea, the Yellow Sea, the Sea of Okhotsk, and of course the Bay of Fundy. These places ring. When resonance builds the range, bottom friction skyrockets and tidal dissipation spikes. That's extra braking torque on Earth's spin, concentrated in a few hotspots. The global slowdown budget isn't evenly distributed. It's written by shelves and sills. Impact. Those hotspots matter out of proportion. A change in shelf geometry, sediment redistribution, relative sea level rise, even human dredging can tweak how much energy is lost each tide and, by extension, how much torque is applied to the planet. Raise sea level on a resonant shelf and you shift the effective depth, retuning the basin. The break can strengthen or weaken. Over decades, as sea levels climb unevenly and coastlines evolve, the total tidal torque budget shifts. The ancient break isn't static. The ocean is adjusting its own brake pads. Then there are seiches, standing waves in enclosed or semi-enclosed basins set off by storms or pressure jumps. Most are local, but when they couple into shelf waves and barotropic modes, they help shuttle momentum along coasts. After strong low-pressure systems, gauges record oscillations that ring for days. Tiny in amplitude, yes, but persistent and widespread enough to be part of the torque ledger. Add internal tides, gravity waves born where barotropic tides hit slopes, and you've got a cascade of mixing and drag that turns rotation into heat in patchy, powerful ways. Here's a micro story from a steel gray morning off a rugged coast. A coastal engineer checked a moored buoy that had been logging currents and tide phases for months. The software flagged a phase lag creeping in at spring tides, minutes, then tens of minutes off expected timing. The instruments were fine, the bathymetry wasn't. A winter of storms had carved a new channel through a sandbar. The tidal wave now accelerated through a narrower throat, piling up and slipping phase relative to the open ocean. Locals noticed stronger rips. The data showed a shelf-scale resonance slightly retuned, a tiny regional change folded into the grand sum of oceanic torque. Meanwhile, something else was happening across basins. El Niño and La Niña don't just move winds, they restructure currents. During El Niño, the Pacific equatorial current system relaxes and warm water shifts east, changing pressure fields and barotropic transport. Oceanic angular momentum climbs or falls depending on the pattern, sometimes reinforcing the atmospheric signal. In La Niña, strengthened trades spin up subtropical gyres, raising OAM and lengthening the day even if AAM moves the other way. The two fluids rarely pull purely in sync. That's why LOD curves sometimes show muted responses and other times amplify. Complication. Separating oceanic from atmospheric torque in real time takes models and data that talk. We have satellite altimeters tracing sea surface height, Argo floats profiling density, and reanalyses estimating currents. We also have GRACE picking up mass redistribution, but OAM estimates still carry. More uncertainty than AAM. Time services fold them in cautiously, which means ocean surprises still slip through and bend UT1 trajectories without much warning. What nobody knew at the time is how much a changing ocean will change its own torque. As ice melts and freshwater plumes spread, density gradients shift. Western boundary currents may migrate or meander differently in a warming climate. Shelf seas may drown progressively, changing resonance. Every centimeter of sea level rise on certain shelves nudges friction one way or the other. Those nudges multiply by millions of tides right into the long-term slowdown and into the decision to add or avoid a leap second. In the aftermath of each season, you can see a quiet signature, a few tenths of a millisecond added or shaved from the day, traced to a current that sped up, a shelf that rang louder, a storm that set a basin oscillating. The oceans don't shout, they lean. And while they lean, another ledger keeps ticking beyond the surf zone, written in orbital mechanics. The moon's pull set the rules. Its slow drift outward is the long game, and it adds a new wrinkle to everything the oceans do. The lunar ledger, moon drift, earth drift. Follow the money, seconds. The oldest account book we have is the Earth-Moon system, and the entries are written in tides. Every day, the ocean pays a tiny fee in friction. Every year, the moon collects interest as it drifts a little farther away. Laser pulses off Apollo reflectors tell us the number, about 3.8 centimeters per year. That outward spiral isn't cosmetic. It's the record of angular momentum moved from Earth's spin into the moon's orbit, and the receipt is a longer day. Stakes first. This is the only slowdown you can bank on across geologic time. It sets the baseline the rest of our story rides. If you're building a standard for centuries, UTC policy, satellite constellations, calendars that still make sense, you have to respect the lunar ledger or you'll be reconciling errors forever. Every other push and pull is weather on top of this climate. What actually happens is a tidy trade with messy implementation. The tidal bulge, dragged ahead by Earth's rotation, pulls forward on the moon, lifting its orbit and lengthening the lunar month. The reaction torque breaks Earth's spin. Energy is dissipated as heat in shallow seas, but angular momentum is conserved. Orbital up, spin down. The magnitude of that break depends on how and where tides lose energy, which is why coastlines matter. But even if the geography changes, the sign of the trade doesn't. That's why fossil clocks and ancient scribes agree. Go back to those corals. In Devonian reefs, you count roughly 400 daily bands per annual ring. Fewer hours per day, more days per year. That's not the year changing, that's the day shrinking. Eclipse records add the human testimony. When researchers project modern orbital mechanics backward and then compare to eclipse reports carved into Chinese oracle bones and Middle Eastern chronicles, the math only works if Earth's rotation has slowed since then. The moon's recession and the lengthening day are entwined, and both show up in independent lines of evidence. Impact. Over billions of years, the free days have been spent. Early Earth spun so fast that a day lasted on the order of 17 hours. Now we're near 24, and the trend continues. But there's the wrinkle that keeps catching people. Today's slowdown isn't smooth. In the last few years, we saw the average day dip under the textbook, 86,400 seconds before water, and winds nudged it back. That doesn't contradict the lunar ledger, it rides on top of it. Think of the moon as the long-term trend line and climate plus core dynamics as the decadal noise. Timekeepers can't plan with a straight edge. They need both layers. Meanwhile, something else was happening along the coasts. The same moon that powers the tides is getting help, or hindrance, from changing shorelines. As sea level rises and shelf seas deepen, some basins shift closer to their resonant periods for the dominant tidal constituents. Where resonance strengthens, friction increases, and the lunar torque on Earth's spin grows. Where resonance weakens, the break eases. The irony is sharp. The moon supplies the forcing, but humans, by melting ice and altering coasts, are subtly changing the mechanical advantage of that forcing. The long game is lunar, the tuning is ours. Why lunar torque isn't the whole story today comes down to timescale and geography. Over the last few millennia, glacial isostatic adjustment, the slow rebounding of land freed from ice, has actually shortened days slightly by moving mass inward. That's a counter-term to the lunar break. On decadal scales, the core's exchange can shave or add a millisecond. On interannual scales, AAM and OAM dominate. But none of these reverse the sign of the billion-year trend. They just modulate when the next clock correction becomes urgent. There's a cultural layer here too. For most of human history, noon meant the sun high overhead. The lunar ledger is why that simple definition can't hold perfectly for long. If we stop inserting leap seconds, civil time drifts off the sun by seconds, then minutes, then more. Some argue that's fine. Computers don't care where the sun is in the sky. Astronomers, navigators, and traditions that key to solar time do care. The moon, indifferent, keeps writing in the margins. Now follow the practical money. Seconds in software. Leap seconds exist because of this ledger. When the day lengthens faster than atomic time accumulates, UT1 slips and UTC must jump. When the day shortens, a negative leap second would be required. The recent debate over abolishing leap seconds is really a question about how often we settle the moon's account in our civil books. Settle often and you risk outages. Settle rarely and noon drifts from noon. Either way, the lunar balance accrues. Complication. The rate at which the moon's steel spin isn't constant in the modern era because the brake pads, shelves, straits, sills are being remachined by sea level rise and engineering. Models that estimate the secular tidal torque must approximate dissipation in poorly observed regions. That uncertainty sits right on top of policy choices for UTC. You can see why timekeepers want fewer emergencies and more planned reconciliations. In the aftermath of each leap second, someone always asks, can't we just ignore the planet and stick with perfect atoms? The lunar ledger answers that. You can ignore it for a while, but the error accumulates. Our choice isn't whether to pay, it's how and when. And the cost isn't just technical, it's social, cultural, navigational. We've mapped the players, the moon's torque sets the background slope, the core, sky, and sea draw wiggles on it. Humans tilt the table with water. We followed the physics to the threshold where physics hits policy. Now step into the arena where seconds are negotiated like currency, and a single bad tick can freeze a market. The second is a battleground, UTC, GPS, and chaos. Follow the money to where seconds settle trades, route planes, and steer tractors. Time isn't a single stream. It's a braided river of standards, each with its own rulebook. Coordinated Universal Time, UTC, is what your phone shows. International Atomic Time, TI, is the raw count from atomic clocks, never adjusted, never pausing. GPS time is time minus a fixed offset, and crucially, it ignores leap seconds. The result, they tick together, but they don't agree on the date of a second that's been added or removed. Stakes first, every satellite position, every financial timestamp, every TLS certificate, every log file relies on a consistent timeline. When two systems disagree about whether a second exists, causality breaks. Events appear out of order, queues deadlock, failovers trip. In 2012, when a positive leap second arrived, major platforms seized because their kernels hit an edge case they barely tested. In 2017, a DNS provider's code concluded time moved backward and crashed a chunk of its network. Those were single-second decisions rippling through millions of machines. What actually happens on a leap second night is a choreography with too many choreographers. The International Earth Rotation and Reference System Service announces a leap months in advance. At 23:59 and 60 seconds Universal Time Coordinated, UTC inserts an extra tick. TI does nothing. GPS time does nothing. Some operating systems step the clock. They literally repeat a second or jump. Others smear the change, spreading the extra second over hours so time doesn't stutter. Smearing works within a closed system. But if your cloud smears and your customer steps, your timestamps diverge in subtle, nasty ways. The internet is a patchwork of these choices. Impact. Distributed databases see the same transaction happen in two different orders. Airline reservation systems miss sequence requests. Authentication services that rely on strict monotonic counters reject valid tokens. Kernel timers, built on assumptions that time increases, collapse into tight loops. Even when an ops team sees it coming, the fix is fragile. One unpatched library, one misconfigured time daemon, and a subsystem goes sideways. After the 2012 event, engineers published postmortems like crime scene sketches. One line kept repeating, "We didn't test this path." Meanwhile, GPS keeps its own counsel. The constellation's onboard clocks run GPS time, which has been steadily diverging from UTC since 1980. Receivers convert GPS time to UTC using a broadcast offset. If that offset is wrong or lagging, your phone still finds itself, but the timestamp attached to that fix disagrees with UTC. Multiply by fleets of drones, survey gear, precision agriculture rigs, and you get a landscape where position and time can drift apart by seconds, then meters. The Earth orientation parameters that tie satellite frames to Earth's spin must be ingested alongside LEAP. Announcements. Miss Either and guidance software aims at yesterday's Earth. Politics enter because seconds decide winners and losers. Telecom and cloud operators argued that leap seconds cause more harm than they prevent. Their systems crave continuity. Astronomers, navigators, and some national labs argued that civil time should stay close to Earth's rotation. After years of debate, the Weights and Measures community voted in 2022 to loosen the leash by or before 2035. In practice, that means UTC can wander farther from UT1 without a leap. The impulse shock stop, a future reconciliation, maybe a leap minute, arrives with decades of warning. Here's a micro story from a midnight operations bridge. A global cloud provider rolled out a leap smear window across hundreds of regions. Traffic was balanced, error budgets padded. 15 minutes in, alarms lit up in the European cluster. A subset of customer VMs had pinned their time to external NTP servers that stepped instead of smeared. The provider's control plane saw two timelines at once. Locks hung, metadata stores split brain, and autoscalers tried to fix phantom load by booting instances stuck in the wrong second. An SRE on duty yanked a circuit breaker, isolated the region, forced all clients onto the smear, and the system rejoined reality. 27 minutes later, the board went green. They filed the postmortem under leap hygiene. Complication: negative leap seconds. We've never removed a second from UTC. The code paths are even dustier. Some kernels interpret a backward step as a fault. Some databases assume unique timestamps. If 59 never happens or happens twice, index is corrupt. Time series systems trained on positive leaps can't generalize. Standards bodies have warned that negative leaps are never foreseen or tested, which is how you spell outage. And yet, the best technical solution, abolish leap seconds, creates a new social debt. If we let UTC drift, noon slides off the sun. In 50 years, the mismatch is still small. In 100 or more, it's noticeable. Astronomers adjust easily. Software can map UT1 to UTC. But public timekeeping has always been a handshake between the sky and the clock. Breaking it quietly changes what time means outside of labs. What nobody knew even a decade ago is that climate and groundwater policy would modulate this battleground. The timing of a negative leap second now depends partly on ice and aquifers. Deep Earth dynamics might speed the crust, but water moving mass outward slows it back. The decision to add, subtract, or wait isn't just physics, it's governance. In the aftermath of the 2022 vote, many breathed easier. Fewer leaps mean fewer nights where 1 second threatens the stack. But the hidden dependency remains. All those systems still ingest UT1, EOP updates, and offsets. The choreography continues, only with longer pauses between hard steps. Abolishing surprise seconds doesn't abolish Earth. The planet keeps editing the script. Now we step into the next scene, where the world tries to legislate away surprises and kicks the problem to our grandchildren. Abolish the leap. Kicking the can to 2135. The 2022 vote landed like a cautious truce. Timekeepers, after years of midnight fire drills, agreed to change the rules of the game by or before 2035. The idea wasn't to fix Earth, it was to stop letting Earth ambush software. Instead of forcing UTC to stay within a razor-thin plus or minus 0.9 seconds of UT1, the plan would widen the tolerance so civil time could drift farther from the planet's rotation for decades. Then, once in a generation, we'd reconcile with a bigger plan correction. Benefits first because engineers wrote them on whiteboards in bold type. Stability for critical infrastructure. No more 23 hours, 59 minutes, and 60 seconds landmines that have been known to crash kernels and confuse schedulers. Cloud providers could smear or not smear on their own cadence without scrambling for every bulletin from Paris. Telecom networks could simplify timing distribution, trusting a monotonic UTC that never stutters. Financial exchanges could stop worrying about trades stamped in a duplicated second. GPS and other constellations could keep their independent times with fewer conversion traps. The leap second era taught a harsh lesson. Extremely rare events are the ones your tests miss. Behind that relief sat a quiet admission that we'd be accruing a debt. Every year, the moon, the winds, the oceans, and the mantle will push UT1 and UTC apart by a handful of milliseconds that no one reconciles in real time. Over a century, that's not hours, but it's not trivial. Noon on the clock drifts from noon in the sky by tens of seconds, then more. The plan effectively kicks the can to 2135 or whatever year the new tolerance runs out. Whoever inherits it will choose a big move. A leap minute, a set of leap minutes, or some sleeker reform we haven't invented. Consequences land outside server rooms. Civil time has always been a social contract between the heavens and the city. Letting UTC walk away from UT1 means public noon is less tied to the sun over your street. Most people won't notice 40 seconds in a lifetime. Astronomers will, but they can map UT1 directly. Pilots and mariners already carry tables linking the sky to the clock. Prayer times, which depend on the sun's angle, are computed from the local celestial geometry, not a wall clock. The daily rhythm of culture can absorb the drift as long as the relationship stays published and trusted, but meaning nags. For centuries, we've tried to keep civil time anchored to Earth's rotation, even as we invented better clocks. A widening gap forces a quiet shift in philosophy. Time becomes something we define and disseminate, with Earth's spin as an input rather than a master. There's humility in that, and a little loss. It's the difference between a church bell that rings at noon and a server farm that says noon is when the packet says it is. Politics didn't disappear with the vote. Some nations wanted to preserve leap seconds indefinitely, arguing that their astronomical and navigational communities depended on a tight UT1 UTC tie. Others, led by industry and supported by national labs, argued that discontinuities in UTC jeopardized safety and commerce. The compromise was procedural. Instruct the metrology community to design a new maximum UT1 UTC difference, implementable by 2035, that ensures UTC continuity for at least a century. That's diplomacy speak for buy time, then hand future timekeepers a bigger wrench. The hidden engineering continues either way. Even if UTC stops leaping, satellites still need real-time Earth orientation parameters. Space doesn't care what we rename our seconds. It cares where Earth's axis points and how fast it turns. Ground stations will still download UT1, UTC offsets, and polar motion updates. GNSS receivers will keep translating between GPS time, Galileo time, BDU time, and UTC. The pipeline of orientation data remains a lifeline, just decoupled from the civil clock step. There's also a plan B none of the committees want to talk about often: leap minutes. If we let the difference grow to, say, 60 seconds, then reconcile in a single scheduled event, everything gets simpler to test. You can plan years ahead for the minute with 61 seconds or the minute with 59. You can stage a global rehearsal. You can force every library to run the code path in daylight with humans watching. You can even decide to do it at a quiet hour or spread it like a controlled smear that's universally agreed. Still, kicking the can assumes the can won't roll back. The specter of a negative leap second hasn't vanished. If deep Earth processes and atmospheric patterns conspire to speed the crust for long enough, UT1 could creep ahead of UTC, faster than the new tolerance anticipates before the reform is in place. That's why timekeepers stress urgency. The new rules need to be implemented cleanly before the old rules force a correction nobody has ever executed. Meanwhile, people in charge of water, energy, and climate policy
probably don't know their players in this drama, yet their decisions will modulate the drift that determines when the next generation faces the big reconciliation. It's an odd kind of responsibility. Turn a valve in a drought, and you've moved a fraction of a microsecond per day. Do it for decades, and you've nudged the calendar. The plan to abolish the leap second doesn't end the story. It changes the cadence. We trade frequent, chaotic jolts for rare, choreographed surgery. We accept that civil time will slide slowly from the sun and promise to bring it back on a date you can print on a poster. It's sensible. It's also a bet that our grandchildren will have better tools and fewer outages when it's their turn to pay the bill. Space is unforgiving. GPS, Galileo, and relativity. Space strips excuses fast. A satellite doesn't care that your code prefers smooth time. It cares about nanoseconds. GPS, Galileo, BDU, GLONASS, each constellation runs on atomic clocks that drift unless corrected by relativity and tied to Earth's wobbly rotation. A billionth of a second is about 30 centimeters of range. Stack a handful of them wrong and a runway centerline slides. Stakes first, precision agriculture steers tractors along 5-centimeter paths. Surveyors certify property lines to the millimeter. Aircraft rely on augmented GNSS for approaches in fog. Autonomous machines feed on fused inertial and satellite time. If the clocks upstairs and the Earth orientation parameters downstairs don't match reality, guidance software aims at a ghost. What actually happens on orbit is a small miracle of bookkeeping. Each satellite carries rubidium or cesium clocks, pre-offset for Einstein's rules. Special relativity slows them because they're moving fast. General relativity speeds them because they sit higher in a weaker gravitational field. Net effect uncorrected is tens of microseconds per day. Engineers bake a frequency bias into the clocks on the ground so they tick at the right rate in space. Ground control uplinks further corrections constantly.
Meanwhile, the constellation broadcasts almanacs and ephemerides where each satellite thinks it is and how its clock is behaving. Receivers on the ground listen to at least 4 satellites and solve for position in time. But there's a catch. That time is the constellation's own. GPS runs GPS time. Galileo runs GST. Baidu runs BDT. None of them insert leap seconds. Your receiver maps satellite time to UTC with a live offset field. Get that offset wrong or stale, and your position lands on the wrong second. Impact. You don't just miss by a meter. Your timestamped fix claims to be now when it's actually just before now. And any system that joins data, ADS-B aircraft tracks, ship AIS positions, traffic flow, can't stitch a coherent picture. In a control tower, that looks like targets stuttering. In a trading engine, it looks like orders arriving out of order. In a combine harvester, it looks like a row that snakes by a few inches, then a few more. While this dance happens, the planet keeps sliding its chair. UT1, the true rotation angle of Earth, meanders. To tie satellite positions to a runway on a spinning, wobbling planet, receivers need Earth orientation parameters, the UT1, UTC difference to nail the rotation, polar motion to nail the axis, precession, nutation to nail the celestial frame. Those parameters flow from VLBI and other sensors through the IER's pipeline, then into navigation services. Miss an update and your world map is a fraction of an arcsecond off. That's meters on the ground. Here's where it gets human. A survey crew sets control points for a new bridge. They're on a tight bid, 5-centimeter RMS or they eat the overrun. The week had high winds over the Pacific, AAM spiked, and the UT1 prediction bent. Their rover pulled GNSS corrections from a network whose reference station hadn't ingested the newest EOP bulletin. At the end of the day, the tie-in closed with a 5-centimeter bias. No one noticed until the steel showed up and the bearings didn't sit. $1 million weekend pour became a rework order. The postmortem didn't blame relativity or the core. It blamed a stale parameter file. Complication: multi-constellation receivers reduce vulnerability but raise complexity. Merging GPS, Galileo, and Baidu improves geometry and resilience, yet each brings its own timescale, intersystem biases, and differential code distortions. High-end receivers estimate and remove those biases, but only if their firmware keeps up with broadcast changes. Leap-second abolition helps by stabilizing UTC, yet the need to map satellite time to civil time and civil time to UT1 doesn't go away. Meanwhile, augmentation layers add their own timing demands. WAAAIA, EGON, MSAS, GAGAN, satellite-based augmentation systems, broadcast corrections from geostationary relays. Real-time kinematic and PPP RTK services push centimeter-level fixes over cellular links. These streams depend on tightly
synchronized ground networks. A hiccup in a timing chain at a single reference station can leak bias into thousands of rovers. The network's phase noise becomes a farmer's crooked row. Relativity isn't a one-and-done correction either. Orbital eccentricity, solar radiation pressure, thermal effects, clocks wander. The ground segment watches every satellite's clock against a composite time and nudges models. During solar storms, ionospheric delays surge and timing jitter jumps. The best receivers use dual or triple frequencies to peel the ionosphere off, but even then, the truth is in the updates. What nobody knew when GPS went operational was how tightly civilian life would couple to these pipelines. We routed planes and tractors and data centers through nanoseconds, then tied those nanoseconds to a planet that won't sit still. The 2022 decision to retire leap seconds reduces one category of surprise, but it also shifts burden downstream. EOP, updates must be even more reliable, clock ensembles more robust, and firmware paths for offsets more thoroughly tested. In the aftermath of each quiet day, nothing happens, and that's the point. The clocks tick, the parameters arrive, the receivers converge, and a machine lays a perfect line through a field that curves with the Earth. Space is unforgiving, but it is manageable if you never let your guard down. The moment you do, reality moves, and your map stops matching the world. Cascading futures, climate, water, and the planet spin. Look ahead, and the ledger gets messy fast. Climate change doesn't just redraw coastlines, it rewrites the torque budget. Accelerated ice loss from Greenland and West Antarctica moves billions of tons of mass from high latitudes to the oceans at lower latitudes. Megadroughts push cities and farms to pump deep aquifers, shipping that water ultimately to the sea. Each transfer pushes mass outward from the spin axis, increasing Earth's moment of inertia and slowing the crust by microseconds spread over years.
Stack enough of those moves and the background slope of UT1 bends. Stakes first. Everything that depends on the cadence of UT1, GNSS, Earth observation, satellite pointing, global finance timestamping, aviation procedures, now sits downstream of climate policy and water management. The timing of a future correction to civil time isn't just a question for meteorologists, it's a function of how fast ice melts, how much groundwater we mine, and how oceans redistribute that load. What actually happens in plausible scenarios isn't abstract. Picture a decade where Greenland's loss accelerates under persistent summer melt, West Antarctica's vulnerable basins keep sliding, and South Asian megadroughts trigger sustained aquifer withdrawals. Graceful maps would paint a steady blue over the oceans and red over emptied basins. Altimeters would see a sea level rise pattern skewed by winds and gravity. After we subtract the fast AMA-ohm wiggles and correct for glacial isostatic adjustment, the LOD record would carry a clear, slowly rising component. The leap second conversation, once threatened by a negative step, could flip back toward postponement, then toward a possible positive step in some future decade if we keep moving mass outward. Meanwhile, coast geometry evolves. Rising seas drown portions of continental shelves, shifting tidal resonances and amplifying friction in some hotspots, reducing it in others. The Bay of Fundy's tuning shifts with shoreline shape. The North Sea's dissipation moves with depth changes. Indonesian passages alter their choke. Those local retunings compound across millions of tides, slowly changing the global tidal torque. Today's estimates of the secular lunar break include large uncertainties because they depend on these dissipative maps. In a warmer world, those maps won't hold still. Impact. Policy joins physics. A region's decision to bank water underground during wet years and withdraw during dry years changes terrestrial water storage seasonally, but repeated depletion imposes a secular drift in mass distribution. Over decades, that drift becomes a term in UT1. Build new reservoirs and you concentrate mass, sometimes closer to the axis. Drain aquifers and you push mass toward the equator. It's local survival with global consequences measured in timing labs. Feedbacks make the ledger nonlinear. A warming ocean shifts tropical convection zones and jet streams, changing AAM statistics. Altered winds feed back on ocean circulation, changing OAM. Both modulate how sea level stacks against shelves, retuning tides yet again. The atmosphere can hand the crust tenths of a millisecond in weeks. The ocean can lean on the crust by similar amounts over seasons. Water redistribution adds a slow baseline. The core adds a decadal pulse. The result is interference. Sometimes the signals cancel, sometimes they reinforce, sometimes they hide each other until a threshold tips. Build a risk matrix and the axes aren't comforting. On one
axis, low probability timing shocks, an unprecedented stratospheric warming that flips the zonal wind field for weeks, a cluster of volcanic eruptions that cools and shifts circulation, a year with both a major El Niño and rapid Antarctic mass loss. On the other axis, infrastructure fragility, untested negative leap code paths lingering in kernels, EOP distribution pipelines with single points of failure, GNSS augmentation networks with lax timing discipline, financial exchanges that haven't rehearsed large offset transitions. Multiplying axes is where outages live. Here's a plausible chain. A warm decade drives high AAM variance and elevated OAM, UT1. Predictions drift more than usual. At the same time, a drought accelerates groundwater exports in multiple breadbaskets. The IER speeds more frequent UT1 updates. Some downstream systems lag in applying them. A busy airport relies on augmented GNSS for low visibility approaches. One receiver fleet holds stale EOP by 24 hours and shifts position by decimeters on final approach. Controllers catch it and raise minima. No accident, but capacity drops, delays ripple. Hours later, a trading venue sees small timestamp skews between colocation racks because one subnet's NTP is pinned to a drifted stratum. Auditors flag trades out of sequence. Again, no crash, just attrition, cost, and a growing sense that time is frayed. Complication. Adaptation can cut both ways. Smearing seconds instead of stepping them reduces leap night chaos, but it hides divergence during the smear window from systems that expect hard UTC. Tightening UTC, UT1 coupling with more frequent microadjustments would improve astronomical alignment but reintroduce software landmines.
Abolishing leap seconds simplifies civil time, but forces universal discipline in mapping UT1 for anything that cares about the sky. Each choice redistributes risk. None erases the physics. What nobody knew even 5 years ago is how quantifiable these drifts have become. With GRACE-FO, with dense GNSS networks measuring crustal motion, with improved AAM-OMAM forecasts, we can attribute slices of light change to water, air, and sea with growing confidence. That pushes responsibility outward. It's no longer acceptable to treat timing as a lab's problem. Water ministries, grid operators, aviation authorities, exchange regulators, they're all stakeholders in UT1. In the aftermath of each year, the LOD curve will carry a signature of our choices. Melt a little more, pump a little deeper, retune a shelf, and the line bends. The invisible force isn't just geophysics anymore, it's policy with a torque. When seconds kill, near misses, and real failures. We've talked about the physics. Here's what it feels like when a second misbehaves and the world blinks. On a winter night in 2012, a positive leap second slid into UTC. In a Reddit ops channel, CPU graphs spiked like heart monitors. Linux boxes locked up as a timer subsystem decided time had moved backward. Sleeping threads all woke together. CPUs thrashed. Reddit went dark, and it wasn't alone. LinkedIn, Yelp, parts of Mozilla, and an airline booking system struggled. In Australia, Qantas crews switched to manual check-in as flights stacked on the apron. The problem wasn't malice, it was a code path almost nobody exercised, triggered by a single legal second. The pattern repeated in smaller waves. In 2015, another leap second. Instagram, Amazon, Netflix saw weirdness. Postmortems read like detective stories. A scheduler assumed monotonic time. A library cached leap status and went stale. A lock waited on a timestamp that never arrived. Engineers patched kernels, taught NTP daemons to behave, and wrote runbooks. But the lesson stuck: almost never is the worst test plan you can have. Then came 2017. Cloudflare's public DNS hiccuped when internal software compared two clocks and decided that time had reversed, a condition it hadn't been taught to accept. Some customers' resolvers went offline. The fix was simple once you saw it. Don't assume time can't step back. Treat time like a stream that might ripple. But the outage still wrote itself onto dashboards in thousands of places that never heard the word leap. Power grids have their own dance with time. They live at 50 or 60 hertz, synchronized across huge regions. Frequency errors are their acute worry, but timing underpins state estimators and phasor measurement units that watch the grid's heartbeat. A few microseconds of skew between PMUs can flip a model from stable to alarming. During a leap event, a badly configured time source can smear when others step. The grid's picture of itself fractures, and operators face false alarms in an already tense control room. It's not the second that kills, it's the wrong picture at the wrong moment. Aviation lives close to the edge as well. Modern fleets layer inertial systems with GNSS and timing networks. A leap second doesn't move a runway, but a receiver that maps GPS time to UTC with a stale offset can attach the wrong timestamp to a position fix. Feed that into systems that fuse tracks and arrivals look out of phase. Procedures step in, minima go up, capacity comes down. That's a near miss invisibly born from a human decision months earlier to get to that time patch next sprint. Maritime traffic leans on AIS beacons keyed to GPS clocks. When a leap second hits and an onboard time source disagrees with shore, plots jitter. In narrow channels, pilots want smooth tracks. A handful of stamps out of order, and collision avoidance logic gets chatty right where calm matters. Now to a hospital on a quiet June night. The network team scheduled a maintenance window weeks earlier, a routine firmware roll. They didn't notice the upcoming leap second in the IER's bulletin. As the extra tick landed, their Stratum 1 time server stepped. Downstream NTP servers smeared. Some machines ignored both and followed public time. Record systems saw timestamps jump, then diverge. Authentication tokens set to expire now expired a second ago. A cluster managing ICU monitors began rejecting sync messages. A failover controller saw inconsistent heartbeats and started migrating VMs. Nurses called IT because screens flashed login prompts in waves. The on-call engineer recognized the pattern and forced all clients to one time source, then froze configuration changes. Within minutes, the ward was quiet again. Nobody died. The postmortem read like a parable. One missing calendar entry became a night of barely averted chaos. Finance has scars too. Exchanges knit matching engines across halls with nanosecond discipline. A duplicated second can make an order appear to submit after it was acknowledged. Regulators sometimes allow the smear. Auditors don't always agree. Firms now rehearse leap events like fire drills, freeze deploys, verify offsets, pin NTP to internal sources, monitor for skew. Even so, a single rack clock drifting behind its peers can trigger an avalanche of out-of-sequence flags that take days to reconcile. Complications stack when negative leap seconds enter the chat. We've never deleted a second. Some kernels treat backward steps as fatal. Some databases assert uniqueness on timestamp fields and balk when 59 repeats or vanishes. The first time someone tries it at scale will be a live fire exercise. That prospect is one reason standards bodies voted to retire leap seconds. Eliminate the rarest, riskiest triggers. But abolishing leaps doesn't end the exposure. Systems still need UT1, polar motion, and precession. Nutation updates to align orbiting assets to Earth. Those
Earth orientation parameters are their own critical dependency, pushed by the same labs that announce leaps. In an outage at a data center, an EOP feed delay can drift pointing models and survey frames by centimeters to meters before someone notices. Take a mid-size ISP's backbone. During a leap event years back, one Stratum 2 time server fell off its upstream and free ran. Its clients, including a CDN edge and a DNS node, followed it into an alternate timeline. Customers saw stale content, then TLS failures as certificates appeared not yet valid. An engineer rerouted NTP and restarted the bad node. The real damage was cultural. Trust in the company's clock discipline took months to rebuild. The through line: seconds fail at the seams, between standards, between departments, between physics and code. Every near miss is a reminder that time isn't a background service. It's an interface with the planet, and it breaks where we pretend it's just a number. The Timekeepers, people fighting drift. Unknown to almost everyone, a few hundred people keep the planet and our clocks in a fragile truce. Their offices don't look heroic. Cables trail across linoleum floors. Coffee cups live beside vacuum chambers. But when Earth pulls on the minute hand, these are the hands that steady it. Start with the quiet switchboard, the International Earth Rotation and Reference System Service. IERS sits at the crossroads of space and time. Every day, radio telescopes on different continents point at the same distant quasars. Radio beacons so far away, they may as well be fixed pins on the sky. That technique, VLBI, measures the Earth's rotation angle and the wiggle of the poles by timing how a quasar's whisper hits one dish a fraction of a second before another. Correlators crunch terabytes of signal. Analysts turn delays into Earth orientation parameters. When UT1 strays, they're the first to know, and when a leap second is coming, or not, they publish the bulletin that makes or breaks 1,000 runbooks. Meanwhile, a different rhythm hums in national labs. The Bureau International de Poids et Mesures sits outside Paris, weaving the world's atomic clocks into international atomic time. It's a weighted average of hundreds of standards spread across national institutes. NIST in the US, PTB in Germany, NPL in the UK, CRIS, NMIJ, SART, each keeps their ensemble tuned, compares their seconds over fiber links and satellite time transfer, and sends results upstream. Every month, BIPM publishes a new steering of TIE and the offset to UTC. That circular, dry as it looks, moves the heartbeat of the internet. These ensembles are getting sharper. Beyond the cesiums that defined our era, optical lattice clocks trap atoms like strontium or ytterbium in grids of light and count transitions that tick hundreds of trillions of times per second. They're so stable that gravitational redshift across a staircase shows up as a measurable frequency change. Timekeepers are preparing to redefine the second around them. That future second won't fix Earth's wobble, but it will make the comparison cleaner. Fewer atoms drift. More reality shines through. VLBI is its own human network. Stations in Japan, Europe, Africa, the Americas, Australia spin through schedules that read like travel itineraries for photons. You observe this quasar at 2:14, then that one at 2:19. Weather, power cuts, a misbehaving cryogenic amplifier. Any of it can punch a hole in the sky map. Correlator teams sit through the night watching fringes lock,
then push solutions to IER errors. On the other end, satellite operations teams and GNSS services wait for the updated EOPs like sailors watch a lighthouse. The delay is measured in days, the consequences in meters. Here's a human moment that repeats every few years. A metrologist in a national lab hasn't slept through a leap second since the late 90s. Weeks ahead, she walks a checklist. Firmware versions on time servers, holdover oscillators tested, NTP hierarchies pinned, alarms tuned. She calls the local power utility, they share timing for phaser units, and confirms their plan. She phones the country's air navigation service provider, compares notes, then writes, "No deploys" across a calendar. On the night, she sits with a headset on, watching a line that should either jump or slope, depending on the smear. When the second lands and the graphs stay tame, she breathes once and emails 2 words. All quiet. Not everyone wants fewer leaps. Astronomers in small observatories, navigators who still sight stars, historians of timekeeping, they argue for keeping civil time tied closely to the sky. Timekeepers have learned to translate. UT1 is published, cheap to distribute, and can be piped directly into software that cares about the sun. Civil clocks can drift a little, as long as the mapping is clean. That compromise preserves accuracy where it matters, and continuity where fragility lives. But there was one problem: distribution. UT1, UTC.
Prosets, polar motion, precession, nutation models. None of it helps if it arrives late or corrupted, so labs harden the pipeline. Redundant mirrors carry IER as bulletins. GNSS control segments ingest EOP automatically. Cloud providers run internal time authorities that anchor to multiple national labs over diverse links. Some have built leap smearing as a service with published kernels, so customers and providers smear on the same slope. Others audit time discipline like security. Logs, alerts, drills. VLBI is expanding too. New stations and understaffed longitudes close gaps. Faster recording systems raise bandwidth and sharpen delay estimates. Experiments with optical links promise sub-picosecond comparisons between clocks on different continents. If it works, the sky's pins get even sharper. The planet's rotation angle comes into focus a hair faster, and the lag between Earth's move and our correction shrinks. Education is the unglamorous front line. Timekeepers write guidance papers that sound like shop manuals. Avoid stepping system time. Prefer monotonic counters. Treat leap seconds as data, not events. Never assume time can't go backward. Test every path you've never run. They teach hospital IT teams to pin to a single Stratum 1 source, then fail over deliberately. They teach grid operators to isolate time domains at substation boundaries. They teach developers that timestamps aren't IDs. Meanwhile, they're scouting the next standards fight. If the second is redefined on optical transitions, who distributes that accuracy? Fiber time transfer is beating satellites for stability at regional scale. A future internet might carry time as a protected core service, like power carries frequency. And if UTC drifts from UT1 by minute someday, how will we script the leap minute? The committees are drafting options now because surprises are what break us. In the end, these people don't control Earth. They listen, measure, and translate. They turn a planet's slippage into numbers. A satellite can trust, and a database can survive. When the core breathes, when ice melts, when winds shove, they keep the handshake intact. Quiet work, invisible, most days, except the days when a second arrives and nothing happens because they made sure it didn't. Designing for a slower Earth. We can't stop the torque, but we can stop the outages. Start with code. Never step system clocks. Use monotonic timers for ordering, wall time for display. Treat leap data as configuration, not an event. If you must smear, publish the kernel and window, so partners match your slope. Test a negative leap path in daylight, with chaos drills that force backward steps and duplicated timestamps. Operational playbooks matter. Pin strata to redundant trusted sources. Validate against multiple labs and alarm on skew, not just loss. Stage freeze windows around announce adjustments. Rehearse EOP ingest failures. Simulate stale UT1 and polar motion to prove your guidance. Stack fails safe. Policy pulls levers too. Water management plans belong in the rotation ledger. Track terrestrial storage, report withdrawals, and anticipate sea level fingerprints on tidal dissipation. Educate critical sectors, grids, hospitals, aviation, finance, so timing literacy becomes as standard as cybersecurity.
Build systems that assume Earth will keep editing, meaning not just math. Pull back from the spreadsheets and the satellites and you're left with a simple tension. Time as we live it versus time as the planet makes it. For centuries, we bent our clocks to the sun because that's how a town agreed when to meet. Then we learned how to count cesium's ticks and built a second so smooth that sunrise could never keep up. The drift we've traced, winds, water, mantle, moon, isn't a bug. It's the reminder that time is both a human contract and a physical fact. Here's the human center of it. Midnight is a promise you make to a world of nurses ending a shift, bakers lighting ovens, and parents waiting for a curfew knock. Noon is a bell in a square and a shadow on a sundial that's older than your city. We can detach civil time from the sky, and most people won't notice for decades. But something in us still checks the angle of the light and says now. The choice ahead isn't whether the planet slows, it's whether we honor that feeling in our systems or bury it under abstractions. There's humility in admitting we're passengers. The planet doesn't ask permission to trade a sliver of spin to the moon. It doesn't warn us before the core shaves a millisecond off a season. Ice doesn't melt on a committee schedule. Yet our lives sit on seconds stacked into schedules, contracts, and code. The work of timekeeping, the VLBI beams to quasars, the optical clocks singing at 10 to the power of 15 hertz, the bulletins that slide into networks, translates the world's motion into a language machines can use without breaking. It's a quiet practice of respect. History runs through this. We've corrected calendars before.
Julius Caesar's leap day fixed a drift you could see in harvests. Pope Gregory's skip dates pulled Easter back to spring. Sailors learned to marry sextants to chronometers and found longitude in a moving sea. Every fix hurt a little because it asked people to trade habit for harmony. Today's debate over leap seconds is that same trade pushed into software. We can keep UTC pure and risk outages, or we can let it wander and teach our machines to look up UT1 when they need the sky. Personal stakes hide in small rituals. A clockmaker in an old town sets his front window regulator by a gnomic routine. Check the noon gun, set the pendulum, align the hands to the sun a few times a year. On a late autumn day, he looks up and notices sunset. Now arrives a breath after the hour his grandfather expected. Nothing has broken. The city still runs. But the room feels a shade out of tune. He adjusts the card in the window that explains his hours, close at sunset, and writes a minute's difference. It's not grief, it's attention. Meaning shows up in responsibility too. Every policy that moves water, every design that assumes monotonic time, every education program that teaches an admin how to pin an NTP source. These are moral choices, as much as technical ones. If we treat time as someone else's problem, we let fragile seams fail in hospitals and control rooms. If we treat time as a shared boundary with nature, we build systems that flex instead of snap. The invisible force slowing Earth is unstoppable. The damage from ignoring it isn't. There's another layer, wonder. The same beam that times a quasar's flicker across a continent also tracks Earth's tiny sway. The same clock that hears gravity's redshift across a staircase lets you see a storm bend a day by 1/10 of a millisecond. That's not just useful, it's a way of feeling the planet's breath in your own schedule. You can treat UT1 like a field in a JSON payload, or you can see it as the present tense of a spinning world we happen to live on. So what do we do as days lengthen by thousands and our tools sharpen by billions? We adopt a posture of layered time. Civil time can be smooth and safe for infrastructure. Rotational time can sit beside it, published and easy to pull when you need the sky. Cultural time, bells, prayers, holidays, can keep their alignment by reading from the same ledger. And we tell the truth. We're moving through a long story where the sun and moon still write the baseline and we fit our schedules into the margins. Every 30 seconds, ask if you'd keep watching. Here's the tease we planted hours ago. The invisible force slowing Earth isn't just tides or core flow. It's our hand on the faucet and our code's assumptions. The concern many scientists feel isn't cinematic. It's the fear of brittle systems meeting a world that won't sit still. The hope is that we can choose to be less brittle. One choice remains as days grow longer by milliseconds. Decide what kind of species we are about time. The kind that pretends it's a number and blames the outage when the planet nudges it. Or the kind that listens, translates, and builds calendars, digital and human, that stay in tune with a spinning, breathing Earth, resolution, and broader meaning. The planet keeps editing our seconds. We either design with that truth or watch critical systems break where physics meets code. If you want the deeper thread,
how unseen mass and maybe even dark matter might tug our clocks. Cue up the next episode right now. Subscribe for more true science stories and bring someone who still thinks time is simple. They won't after this.